Hello. Uneka. Hello. Adetu. Fatai. Can you hear me?
We can hear you, sir.
You can hear me?
Yes.
Okay.
Uneka's audio is muted.
Oh, Ojo?
Yes, sir.
What is happening? Is it muted?
Uneka's audio is muted. So
Okay.
okay. She won't get to the platform.
Okay. Wait, I hope I'm on the right platform.
Yes, you're on the right platform. And I've checked other classes. There's nobody there.
Monday. Ojo?
Yes, Monday. Yes,
okay.
Sir.
But there are few, 27 so far.
Yes. The number is increasing. It was initially around 15, 17, 18. So they are entering little by little.
You can also try to quickly check Wednesday and Thursday whether some people are there.
I've checked it. There's nobody there.
Okay, thank you. Okay.
Yes, sir.
So, Uneka.
Progress.
Uneka. Now. Unawo. Can you hear me?
Yes, sir.
Okay. Morning. Okay. You're welcome.
Thank you, sir.
Ojo.
So,
I think there's some echo. I don't know what's causing the echo.
okay, okay, I'll be there.
Okay.
Yes.
Ojo. I think the echo. All this, the YouTube. Yes. So I can go on. Hello. Good morning, everyone. Where do I get it? Yes, sir.
They won't be able to, if they respond,
What are they doing? Hello. Fine. Hello. You can you hear me? Okay. Good morning, everyone. We have already started the second class, and I'll continue from where I stopped. But before then, let me just quickly run through what I taught you the other time. I said the course is divided into 6 broad areas, and each area is going to be taught by a lecturer. And then I started from Unit 1. Essentially, the topic I discussed last week is on the screen: rate of reaction and factors that affect the rate. And I told you that the rate of the reaction and the way the reaction occurs, they all belong to chemical kinetics. And then what does chemical kinetics do? It answers the question, how fast does the reaction go? And what is the mechanism of the reaction? How fast does the reaction go deals with the speed, the velocity, the rate of a reaction. And I did say that when I'm talking about the rate, the velocity, the speed, essentially I'm talking about the same thing. Then I also talk about in detail the mechanism of the reaction. That is the way the reaction occurs. And then this topic, as I said, is under reaction kinetics. So under that reaction kinetics, we deal with the rate of reaction and the reaction mechanism. And I explained to you more about reaction mechanism, more than the rate of reaction last week. And I said it's the molecular event of what is happening to the reactants in their progression to product. Or it has to do with how the reaction is occurring, account of how the reaction takes place, or the summation of all the processes. A process is like elementary step. And then when you add them together, what you get is what we call the balanced chemical equation, or the stoichiometry of the reaction. And then what gave you the stoichiometry of the reaction, the balanced chemical reaction, is the summation of the elementary steps. And when you're giving account of that, you're talking about the way the reaction is occurring, which is a mechanism. And I said that some of the things that will be very common, the key concepts, we're talking about velocity or speed or rate. What we talk about reactants and products. And then later we'll talk about initial rate, determining or limiting steps. So these are some of the things that I will be talking about most of the time. That is why I referred to them as key concepts, that they will be very common. What are the objectives at the end? In this unit, you will learn, or what are the objectives? You will learn about factors that affect the rate of reaction and how to explain the rate of reactions. In this unit will enable you to understand that some of the reactions, they are very fast, some of them are very slow. And then if you know how fast or slow a reaction is, then you'll be able to make use of it. If not, it can explode even before you finish the experiment. So you have to be very careful. If a reaction is very fast, you may not make use of it very well. But if you know how fast the reaction is. Then you can make proper use of it. So some can take even years. If a reaction will take years, then what is the purpose? Why do you want to study it? So we move ahead. And I continue to expected outcome at the end of this unit 1. And I said, you'll be able to define or explain rate of velocity or mechanism of reaction, links the factors that affect the rate of reaction. So I've explained to you what you understand by reaction mechanism, or which fall under reaction kinetics. And the kinetics, it answers the question, how fast and how the reaction is occurring. So let's go into, I'm just repeating most of the things I taught you last week. And I did say that it's not enough to understand the stoichiometry of a reaction and the thermodynamics. These are the things you're familiar with. Stoichiometry, balance the equation. Hydrogen will react with oxygen that will give you H2O. You can balance that. That is what you know. But how did you get to H2O? There are steps that are involved. And there are steps that are involved. So those are some of the things that you will get to know through this topic. So it's not enough to study the stoichiometry and the thermodynamics. It's very important to study the factors that affect the speed or the rate of a chemical reaction. So very quickly, why are you measuring the rate of a chemical reaction? I explained all this to you last week. Then you can download the note and you will find out that what I taught you last week is available. If you go to the platform, you can download it and you get all the information you're looking for. Now, very quickly, what are the factors that affect the rate of reaction? I did say that the nature of the reactant is very important. The reactants are the ones that come together to form the product. In what form are they? Are they solid? Are they in powder form? If you change something to a powder form, you increase the surface area, and it's likely going to react very fast. What about concentration? It does affect the rate of reaction. What about the temperature of the system? It does. What ability of the reactant to come in contact with each other? They need to collide before they can form products. So if they are finding it difficult to come in contact, it will affect the rate of reaction. What about a catalyst? Availability of agents called catalysts. They do affect the rate of chemical reaction. You must have learned something like that during the Haber process in the production of ammonia from school. So these are some of the factors. As we run through this course, we'll take some of them and discuss them in details. And that is what we're going to do. More about the mechanism of reaction, you'll get that if you download the note, and they are there. I ran through all this. Then I use this equation to explain to you the decomposition of the nitrogen pentoxide, and that is up there. But the equation you see on the board or on the screen, the equation you see on the screen is what you call the stoichiometry of that reaction. Is the balanced chemical equation. And then if you want to study the speed of the reaction, you can monitor the rate at which the nitrogen pentoxide decomposes to give you product. And then if you want to study the mechanism, and then you have to work out in details all the steps involved for you to get to this particular equation, balanced chemical equation. So if you want to give account, it depends on how intelligent you are in this area and your experience. For example, I can give account of how I got to the nitrogen pentoxide, or I got to nitrogen 4-oxide and oxygen. Look at the steps you have there. Look at the steps you have there. One step is very slow. That's the first one. Look at that. This one. That step is very slow. As soon as nitrogen 4-oxide and nitrogen, I think 6-oxide, they are formed very quickly. Look at 2. They combine again to give you. So 1 is a step. 1 is a process. 1 is elementary step. So anytime say elementary step, I'm talking about process, it's a step that I've identified. I can work out, I'm trying to work out how I got to the stoichiometric equation. Then again, I can also get another step within the reaction. Look at 3. Another fast step. So some of the steps are slow. It's like, what is your journey to Lagos? If you run into a hold up, that's what you call go slow. And then that will slow the step. That will slow your journey to Lagos. The same thing in reactions. Some steps are fast and some of them are slow. And you can see 1 is slow. As soon as that is established, very quickly, 2 will take place. And then you have that. As soon as you have 2, then you can also get step 3 very fast. 1, 2, 3, they are elementary steps. Take note of the language I'm using. 1, 2, 3, they are processes that led to the formation of the decomposition of the nitrogen pentoxide to give nitrogen 4-oxide and oxygen. Is the summation of the 3 processes. I sum them up, and then what I got is the balanced chemical equation. And that's what you see finally. And 1, 2, 3, they are explaining the way the reaction occurred. And 1, 2, 3 form the mechanism of the reaction. They describe the way the reaction occurred. It gave me the molecular events of what is happening to the reactant, that is the nitrogen pentoxide, to give nitrogen 4-oxide and oxygen. So it's very clear to you now. I can add up. I can deliberately put, look at 2 in front of this. I put 2 there so that I can add up. I put 2 here. If I put 2 here, I should also put 2 here. If you check the way you balance equation in your school, where you're coming from, you find out that 1 is balanced. Then you can add up the 3. Anything on your right-hand side of all the arrows are what you call reactants. And whatever on your left-hand side, you call them, those on your right-hand side, you call them the products. And those on your left-hand side, you call them the reactants. So you add up. When you want to add up, follow the process now. Look at this. I have NO3. Then I will come to my left-hand side. Look at NO3. Look at NO3, 2 of them. Then I go to my right-hand side. Look at this, 2, N03. So they are out. It's not 0 essentially, it's oxygen. So NO3. They cancel the 2 on my right-hand side. We cancel this one and this. So all that are out of the system. Then if I look at my right-hand side, I will see oxygen here. You have no oxygen on my left-hand side. So I will bring this oxygen down and put it here as a product. Again, I will look at NO, nitric oxide, on my right-hand side. Look at that. NO on my right-hand side. I will go to my left. Look at NO. I will remove them from the system. NO, NO, and then NO, NO. They are out. So what is left on my left, you have N02. Look at N02. Okay, or NO2. I will try and look at it. You can cancel this one. N02 or NO2, essentially. So this is out of the system. So what is left? Look at this. Let me pick another thing to explain that. Look at what is left. On my right-hand side, you have 2 of these. Go down, add it to 2 of these. That will give you 4. And this is how I got the 4. Then on my left-hand side, look at this. 2 dinitrogen pentoxide. Look at that. There is no other dinitrogen pentoxide. So I move it down and put it here. That's how I got the balanced chemical equation. This is what you see in school, wherever you're coming from. It's not likely you did mechanism in school. But what you see is the molecular event that happened in elementary step 1, elementary step 2, and 3. Is the totality of all that added that gave me the stoichiometry. So when you are given a description like this, account like this, essentially, you are talking about the mechanism of reaction. We'll meet more of it as we go on. So let's go. Okay. 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 Oh, I need to clear the screen. Pointer. Oh, what is it used to be there. In a minute. Pointer option, user, highlighter. Annotation, maybe from top. Check this. Eraser. Okay. Rates of chemical reaction. Rates of chemical reaction. Only 190. I'm in YouTube. Okay. Okay. Thank you. Adekola, what is your problem? Okay. Chemical reaction. The rates of chemical reaction. So I'm going to start discussing the rate now. I've explained a lot about the mechanism. I'm just repeating what I taught you last week. As time goes on, reactants, they change. You know, I told you chemistry is about transformation. As time goes on, the reactant will be changing to become product. And so you can monitor the rate at which the reactant is changing or the product is being formed. And so you can explain the rate of reaction in 2 ways. I told you that when you're traveling, the distance is like concentration in chemistry, 100 kilometers. Instead of saying 100 kilometers, chemistry will be saying 100 mole per dm cube. And I did explain to you that anytime you see a bracket, a sign like this, it means mole per dm cube. So what is inside here, the reactant, is just the change of the reactant over the time taken for that change. And so you can define rate of reaction in two ways. If you are using the reactant, if you are monitoring the reactant, you put a negative sign in front of the average rate of the reaction. If it is a product you are using, maybe you are monitoring how much of the product is formed, you put a positive sign in front of that. Then the product, what I mean, let's take the first one so that you can understand. If I give you 100 naira, okay, and this morning, after 30 minutes, you find out that what is left in your hands is 80 naira. In other words, you spend 20. So what is the change? The change you get, what is the change? The change is 20 mole per dm cube. That's what you put here, where you have this reactant. Over what time it is now? 30 minutes ago, that I gave you the 100, the over time taking. If it is a reactant, you put a negative sign, because the time rate of change of how you are spending your money is negative because the money is decreasing, but the rate is a positive quantity. So deliberately, so that we don't change the rate of the reaction of the reaction to be negative, we put a negative sign. What I mean is that you say you have 80 naira left, but I gave you 100. In other words, look at the screen very well. 80. How did you get the 20? 80. That is the amount that's left. Take away 100. If you take away 100, what are you going to get? It will give you minus. It will give you minus 20. So because it is minus 20, you are not owing anybody, and then you have a problem. So what we do in defining our average rate of reaction, you put a negative sign there. So minus 20 becomes plus 20. So the rate of a reaction is a positive quantity, but the rate of change of the reactant is a negative. The rate of change of the reactant is a negative value, but the rate of that reaction is positive because you have to put. That's why I say minus 20 minus 20. That will give you 20 over the time taken. But if it is a product, all you need to put is plus because you are forming the product. But in case of the reactant, it is decreasing, but the product is being formed. And that is why amount of the product at the beginning, before you start, a product is 0. With time, the product will be increasing. And then your product is increasing. Therefore, you put a positive sign in front of that definition divided by the time taken for that reaction. So I call that, look at that, equation 1A and 1B. So take note of it. And then you can indicate that the rate of reaction may be defined in two major ways, either in terms of the reactant or in terms of the product. You can use any of them to define the rate of reaction, depending which quantity you can measure successfully. The one you can follow, is it the reactant you want to monitor? Is it easier for you to monitor the concentration remaining at any time? Or is it easier for you to monitor the product at any time? If I gave you 100 and you spent 20, what did you use it to buy? A bottle of Coke. I can see the bottle of Coke. So I can monitor the bottle of Coke of a drink that you bought. Instead of looking into your pocket, I may not know what is left in your pocket. So two ways, you can monitor the reactant or you can monitor the product, whichever one is easier for you. Some reactants, like enzymes, they may be very small for you to follow, but you can monitor what is equivalent to that. And that is why sometimes you can look at the viscosity of the system, or you can look at the refractive index of the system, or you can look at the conductivity of the system, or you can look at the color. And some of you, if you wear a dress that the color is very bright, you'll be saying, where the dye they use in making it is very thick, is very concentrated. You can carry that ideas to your monitoring, to your experimental observation. Of course, we have equipment. We have equipment designed to monitor either it is color or it is viscosity or it is refractive index. Okay, so let me quickly go to look at those reactions, A plus B, and that will give you C plus D. Take note, look at the screen very well. I'm going to define something. What is A? A is an alphabet. What is B? I didn't put any, we don't deal with A and B, but we can use A and B, C, D to represent a molecular species, to represent a reactant, or to represent a product. So what I have there is A. What is the state of A? A is in gaseous state. So that G stands for gaseous state. That is the physical state of A. What is A? You don't know. You don't know whether it is hydrogen or it is nitrogen. What is B? You don't know. But I use it to represent a molecular species. A and B are what we call reactants, those on your left. And then they will react to give C and D. Those on your right, those are what we call products. C and D are products. Whenever you see A, B, C, D, we're using those alphabets to represent a molecular species. You call such a reaction undefined. Please take note. If you are not going to leave this morning, you must learn this undefined. In other words, I did not put anything like a compound that is reacting or a molecule that is reacting, but I use A, B to represent molecules. A can be nitrogen, B can be hydrogen. When they react, they can give me like C, which is ammonia. But when it is A plus B equal to C, it's undefined. But when it is hydrogen plus nitrogen to give ammonia, it is a defined reaction. So take note. Okay, look at that. I want to study this equation. Very quickly, that's equation 2. I want to study it. How do I study it? Is it easier for me to monitor A, or easier for me to monitor B? Or is it easier for me to monitor C, which is the product? Which one is easier for me to determine the concentration that is formed or that has concentration that has disappeared? So this is how you can define your rate. Question 2, expression 2. These are when you want to define the rate. The rate is right for the rate of decrease of A. Anytime I ask you for the rate of decrease of a reactant, you put a negative sign in front of it, minus. That means that reactant is decreasing with time. Then you take some amount of it, it's like a differential expression. For those of you who passed through, who did math also, that is small of the A. I told you that with square bracket, that means mole per dmq. You divide by the amount of time through which the reaction has taken place. And that is minus the A dt is equal. Why is it equal? You can use any of them. You can use A, you can use B as the reactant. So when B is, look at the equation above. B is a reactant. So when you want to write for the rate of decrease of B, you also put a minus sign there. That small d, the D, the lowercase of D, stands for some amount of A. And then you represent A by mole per dm3. Then you divide by the time, the small change in time, and that is the T. It's also equal. You can also use the product. And one of the products is C. When you get to C, C is a product, so you don't put a negative sign there. If you put a negative sign, you are wrong. It's assumed that there's a positive sign here. You don't need to put it. It's assumed it is there. And it's also equal to D. It's also a product. So this is the relationship between them. They are related. Why are they so related? It's easy. Because how many molecules of A are here? 1. How many molecules of B? 1. How many molecules of C form? 1. How many molecules of D? 1. So it's not difficult to write the relationship between the reactant and the product. Therefore, equation 3 is a relationship between the rate of decrease of A and the rate of decrease of B and the rate of formation of C and also the rate of formation of D. That's a relationship that ties them together. Why is this so easy? Because 1 mole of each of them, of the reactant 1 mole, the product also 1 mole. When it is not 1 mole, what do? Look at that. I've just explained that the concentration of A or B decreases during the time interval. That is why I entered a negative sign in front of the A over the T, the B over the T. The significance of that is that the rate is decreasing with time. The concentration rather is decreasing with time. But when I got to C and D, the concentration is increasing with time. So I put a positive sign in front of C and D. Although you now know the significance of that negative sign, that it affects only the reactants. Now let's go. What if A and B are not 1 mole, but 2 or 3 or 4? If it is 2, 3, or 4, and I don't want to write 2, 3, or 4, so I can write something like this. Look at that. A, lowercase of A. That A, small a, it can be 2, can be 3, can be 4. Look at B. B, the lowercase of B can be 2, can be 3, can be 4. So it's not like equation 2 when we entered 1 mole of each of them. To give C and D, when you want to write, this is a general expression. And again, it's undefined. Take note, undefined equation. But if I change A to nitrogen and I change B to hydrogen, then I'm having a defined equation. So equation 4, how do you write the rate? The rate of decrease of A, the rate of decrease of B. When you want to write it, then you have to take care of the stoichiometric factor. The number of moles, the lowercase of moles, small a, is the number of moles of capital A. Lowercase of B, the number of moles of B. Lowercase of C is the number of moles. So whenever I want to write the rate of decrease of A, the rate of decrease of B, the rate of decrease of C, the rate of increase of C, the rate of increase of D, you must take care of the stoichiometric factors. The coefficient, again in school, you know what you understand by coefficient. The coefficient of capital A is lowercase of A, capital B, lowercase of B. So you take care of the stoichiometric factor, the coefficient of the reactant as well as the product. So how can you write a rate expression or the rate of decrease of the reactant and the rate of increase of the product? How can you relate them? Then you tie them together through the coefficient, the stoichiometric factors. Now let's go to the next equation. Look at that, equation 5. In order to write this equation 5, which will not confuse people, then you do it this way. Look at that. Let's start from what you know to what you don't know. Look at that. You know this already. This is the rate of decrease of A. So what do? Rate A is a reactant. So you put a negative sign in front of it. And then what is left? You have, from your mole concept, you have the lowercase of A. So you divide the rate of decrease of A by the coefficient, or what you call the molar coefficient, or the stoichiometric factor. And that's the rate of the reaction. You can use this one to represent the rate of reaction, the whole of this. And then you go to another reactant, B. Remember, B is a reactant. So remember to put a negative sign there, okay? And write the rate of decrease of A divided by the stoichiometric factor. Look at that. And then when you get to C, C is a product. You put a positive sign there. Look at that, it's there, but I don't want to put it. Look at the positive sign, it's there. So you write for the rate of decrease of C, and then you divide it by the molar coefficient. Look at that. Then when you go to D, and then you find that D is a product, so you put a positive sign there. Whether you put it or you don't put it is correct mathematically to us. This one is the rate of decrease from what I taught you before. And then you divide it by the molar coefficient. If you put a minus sign here, the last one, or the one of C, if you put a minus sign in front, it is wrong. They won't give you the marks. So when it is reactant, put a negative sign in front of the rate of decrease. When it is a product, put a positive sign there. When the number of moles are more than 1, let's say if you have something like this equation I've given to you, look at that. Instead of there's no problem. Instead of A, and I have 2A, look at that below, 2A plus, instead of B, and I have 3B. Let me just use that for the reactant for you. And then look at that, 2A plus 3B. And then when you come here, this is what you do. Write for the rate of decrease. Write for the rate of decrease of A. Then you divide this one. Where you have that lowercase of A, what do you put there? You put 2. Where you have the lowercase of B, what do you put there now? You put 3. 3 will be there. So what do you do? dB over dt, 1 over 3. Remember to put this negative sign there. Okay, I've defined those stoichiometric factors for you. They are the coefficient. And so anytime, if I ask you to write for this equation, look at that very quickly. This reaction 4. If I ask you, write the relationship between the rate, you can take it down if you like. Write the relationship between the rate of decrease of A and the rate of formation of C. Write an expression to link. Well, what is the relationship between the rate of decrease of A and the rate of formation of C? This is what you write. This is what you write. The question I just asked you now, you say D into A, okay, over dt, right, for the rate of decrease. Relationship. Remember to put 1 over A. There is a reactant. Put a negative sign there. Equal. Look at that. Equal. A question I ask you, the rate of decrease of A and the rate of formation of C. Then you go to C and say 1 over C. If you like, put a positive sign there. If you like, leave it. They will still mark it for you. D, that is D into C, and over what? dt. This is dt. That is the relationship between those two. If you make a mistake and put a negative sign here in front of this place, a negative sign, then everything you have written is wrong. I give you another one again. Write the relationship between, this is a quiz for you. Take it away. Write the relationship between the rate of formation of C and the rate of formation of D. What is the relationship between the rate of formation of C and the rate of formation of D? Okay, that is a question for you. You can answer it, submit to the platform if you like. Okay, very quickly. Look at that. Let's go to a graph. Some of you will understand the graphical form of okay, look at that. Look at the reaction here. A is reacting to give B. Okay, on top of the screen there. This is undefined reaction. And then I can plot a graph. Take example, A is 100 I have given to you. Just give it any amount you like, whether in Naira or whatever amount, okay? Where did you leave your home? 8 a.m. Call it 0 time. Time. 0 time. This is the time. You left your room and your friend gave you 100 naira. Now you spent about 45 minutes. So put 45 minutes here. 45 minutes. Okay. What is left? What did you buy? Did you enter Okada or something to get here? What is left? 80 naira. Okay. And then towards the afternoon, this 45 minutes or 2 hours after, that is, or 1 hour after, that's 60 minutes. You can change all this to seconds if you like. What is left? 50 naira is left. So that is how we monitor the experiment. Then after a long time, 3 hours, what is left? 20 naira. So what do you have essentially? You have amount of money left in your pocket or in your handbag and the time at that time. If I ask you, look, you came home. I mean, you came to school with 100. Now it is 3 hours after, 3 hours. 3 times 60 minutes times seconds, if you like. How much is left? You give me the amount. And I want to study the speed at which you spend your money. So I will have something like that. So A is like the 100 naira. The 100 naira, it was 100 at 0 time. It is 80 at 45 minutes time because you are spending. Therefore, A is decreasing. If I ask you to write for the rate of decrease of A, you write dA dt because A is a reactant. You put a negative sign there. So what I'm going to do is 100, we say it's 100 mole per dm cube at 0 time, 80 moles per dm cube. Chemistry is not naira again. It is mole per dm cube. So you're going to plot concentration. Look at the concentration. Y-axis against time. And that is the time. Look at this. The time is here. I've given you the time, 0. So this is going to be 0. This is going to be 20, 40, 50, 60, like that. Then this is going to be your amount that is left at any time. So you can, this is when you left home, 0 time, 100 naira. You plot that point. Then after some time, 45 minutes, you plot that point. Then you have a graph like this. That is the reactant. What about the product? When you left home, there was no product. B was not there. With time, what did you use 20 naira to buy? That gave you, that reduce your money to 80. Bottle of Coke, what is it? So that can be product. In chemistry, we are not having Coke, but we are having product. Okay, so you can monitor B. They will all give you this, essentially, they will give you the same thing. So B, why A, your A is decreasing, it's not disappearing. Essentially, it's forming B. So A, so you can plot what is left against time, or what is formed against time. It depends which of them is easier for you to monitor. Once you can do that, then you can take your slope. What is your slope? You know how to find slope. This against this. And that will give you your slope. And that's what we call the differential. And that gives you the slope. That gives you the rate of the reaction. So much per unit time. Or you can use this one. It's a linear plot. At any point where you take the graph from what they taught you in school, if everything goes well, it should give you the same thing. So it's constant. At any point, you determine the slope. Whether the product you are using or the reactant, that will give you the rate of reaction. Later, we're going to study how each reactant does affect the rate of a chemical reaction. Look at that. The graph that I referred to as a linear plot, most things don't go on that way. You know, if I ask you to walk straight from here to UI gate, you are not going to. It is very difficult. By the time you get to somewhere, wherever you are, you're going to meet a structure that can disturb you. So most things can follow a curve. So let me give you another experiment. The first one that I showed to you, at any point where you take the graph, if everything goes well, it's supposed to be constant. It's supposed to be constant because it's a linear plot. But things don't go on that way. Look at another kind of experiment. C is decomposing to give D. This is a defined reaction. C is something like, okay, maybe carbon 4-oxide decomposing or calcium carbonate, maybe decompose something. It's not defined. It's just an example. So what happened with time, C will be decreasing. With time, D will be increasing. But it's like the joy you experienced when you got your admission to UI. Now, how is that joy? Is it increasing or decreasing? When you find out that you need to attend lectures, you need to write tests, you need to write exams, say, it is good to work very hard. So instead of thinking of the happiness of admission, you're thinking of something like how to write your exam, write tests, attend lectures. So it's the same thing with all this. Look at C. With time, C is decreasing. And now it's coming down like this. Okay, but this time it's not linear, it's a curve. And then as C is doing that, it's not disappearing, it's forming D. If you plot D that is formed, it will give you like this. This, what is the graph you see there, is a curve. If you take the slope of D around here, is different from the slope at this point. Okay, as you go, if you take the slope here, you take a point, and then you draw a target, and then take the slope, okay? You find out that from here to the slope will be changing because it is a curve. So reaction rates are like that. At the beginning, you were so happy. Reactions rate at the beginning, they are very high, but with time, they will be decreasing. They are decreasing, it is because you are forming more of the product. The product can even disturb the reaction. There could be side reactions. So it will affect it. And some of them, they will run it towards equilibrium. And another lecturer will be telling you that story under equilibrium. It's something like dynamic equilibrium or static equilibrium. Okay, so they run it towards, they will level up like that. Not that they have disappeared. They can still be going on. You have a dynamic system going. So this curve is going like that. If you go on for a long time, you see that it will level up. If you take a slope here, it's likely to give you 0. So the reaction will be changing and it's higher at the beginning. So after some time, maybe the next class we'll be talking about initial rate of a reaction. It is because the initial rate is very important in interpreting the speed of chemical reactions or comparing reactions. So this graph you see now is curved. And then with time, you can determine the slope at any point. You can have instantaneous rate at any point because that will give you the differential. This is a non-linear plot. The first one is a linear plot. But now let me give you an example and see how you're understanding. In 300 seconds, the concentration of A falls from this concentration. Look at the mole per dm cube to 2.5 times 10 minus 2 mole per. So it's decreasing, A is decreasing. And this is the reaction. See the reaction on the board. What is the rate of the reaction? Look at what I'm telling you. From here to Lagos, 300 kilometers. From here to Lagos, it took you 300 seconds. What is your speed? 300 kilometers over 300 seconds. That will give you 1 kilometer per second. Oh yeah, put it here. This is what you started with, 3.4. It has now decreased to 2.5. What has changed? What is the change? It's 3.4 minus 2.5. And then when you get that change, you divide it by 300 seconds. So it will give you the rate of the reaction is so and so mole per dm cube per second. If you don't get the right unit, they will not mark it for you. It looks simple. Now let me ask you another one. From all that I have been describing, I'll be telling you. Look at equation 2. Which term describes the measures of the increase in concentration of a product per unit time? Is it like rate? Is it kinetics? Don't get confused. Don't get confused. Is it activation energy? You know activation energy when you talk about the endothermic reaction. We haven't reached there, so this A is wrong. Is it kinetics? Kinetics addresses two things that I taught you. But I'm asking you, which term describes the increase in concentration of a product per unit time? Is the rate of a reaction or reaction time? What will be your answer? You just pick one. If you pick kinetics and kinetics is not the answer, you know your exam is OBJ. They will provide answers. It's democratic. You have the right to choose. If you choose B instead of the right answer, that is the end of that. So I've just used these two questions under quiz number 1 to test you. Are you following? How can you calculate the rate? The first one will tell you is the change. It has decreased by so amount. Okay? Then you divide it by the time. Don't put negative sign in front of it. Don't put negative sign in front of it. This is like the last one is like 80. This one, that is 80. This one is like 100. So don't go and say it is 80, take away 100. When you subtract it, you don't need the negative sign again. Just divide it by the time, and that will give you the rate of the reaction. I have another one. I don't know how I can get this. I wanted to decrease this. Okay. Let me leave it. Okay. I think they should be able to see this. It will be too much for them. Okay. I think let me leave it like this now. Okay. Let me leave it. Okay. Then this is okay. This is the book. There's a book. You can see it as a university bookshop if you go there. Fundamental Physical Chemistry. And once you ask for it, or you go to the publishing house of the University of Ibadan. It's opposite Faculty of Pharmacy. Publishing house is where you have maintenance department. They have a publishing house there. You can stay at the one that published the book. You can see it to buy there. Okay. That is, what is that? 9:59. Okay, I want to answer some of their questions. So I have gone through Unit 1. So when we meet again, by the grace of God, it's going to be faster. So if you have a question.
Time for question, please raise your hand.
Yes, ask Muturayo. What's your question?
Sir, please, you said something about a test that is given to us. So how are we going to submit?
Did I give you a test? Quiz?
You said so while during the class.
Quiz, you can submit now. Go to the platform. You don't know how to submit?
Sir?
You don't know how to submit your quiz?
Yes. No, sir, we don't know how to do it.
Okay, just do it. I'll give it to your friend to check it for you. Okay?
Okay, sir. Okay, sir.
Is that the only question you have?
Yes, sir. And sir, there are some people that are unable to access the class, like we are together. The site is asking for registration or something, so we don't know.
Just key in your matric number and enter. How did you enter yourself?
This one was just a direct, like when I click on the link.
I used
you click on the
one
link.
I registered for last week.
Yes.
Yes.
But some will be asking for registration.
Bye.
Don't you have matric number?
We have matric number, sir.
Put matric number and your email, and it will allow you to come in so that we can take attendance. Okay.
Okay, sir.
Any other? Who is this now? Olari. Olari, why'd you
Yes, sir.
ask your question?
Sir, I have a question. Regarding the question you gave us, you said, what is the rate of formation of C and rate of formation of D? Sir, I don't quite understand.
What is the rate of formation of C and the relationship, the rate between the rate of formation of D and the rate of formation of C? What is the relationship between them? Appearance of A and the rate of formation of C. I gave you the answer to that. And I said, right, for the rate of formation of C and the rate of formation of D. Can you do that?
No, sir.
It's very clear now. You write C and D, they are products. So put a plus sign in front of any of them. And then write for the decrease of the increase of C and equal to the rate of increase of D. Did you get it?
But I didn't give us any moves.
For the, what do you mean by didn't give you? For which one did I ask you? Is it equation 4? I didn't give you. C is the,
When you gave us 2A and 3B, you said you should use -1/2 for those ones. But you didn't give us any
those
moves.
are the number of moles. But this one I'm giving you now. I didn't give you any more. I just gave you lower case of A times A plus lower case of B times B equal to lower case of C times D plus lower case of D times D. So the number of moles, they are just A, lower B, lower C, lower D. So where you have, so that those are the ones you use in dividing, okay?
Okay, sir. But sir, actually, this is not the person talking. I came to tag along because I was unable to log in to join the platform.
You were unable to log in. Where are you?
I'm with my friend, the person bearing this name. We are both listening to this.
Are you in school?
Yes, sir.
You can come to room 5. We'll tell you how to get to the platform, okay?
You can come to where?
Room 5, chemistry. We will tell you how to get to the platform.
Okay, sir. Okay, sir.
Okay.
Thanks, sir.
Okay. So on Wednesday, please use the link for Wednesday. Or if you can't link with us, go to the YouTube. There is a link. Again, go to the platform, the LMX platform. Go and copy the link and join the YouTube. Many of you are on that platform. And if you can't get to us, go to YouTube. So have a great day.
And you too, sir.
Okay.
I'll be like bicycle.
Whatever life.
Clearly.